Good morning. It's August 29th, and this is your daily brief in science. Here's everything you need to know. Researchers at the University of Pennsylvania have demonstrated the transmission of quantum signals over existing commercial fiber-optic cables using standard Internet protocols. This marks a significant step toward practical quantum networking. Their tests on Verizon's campus fiber network showed that fragile quantum signals can coexist with classical Internet traffic on current infrastructure. This development suggests that future quantum Internet could leverage existing network technology to accelerate deployment. The experiment involved transmitting quantum information through classical Internet protocols, routers, and fiber-optic cables. Quantum Internet promises secure communication and the linking of quantum computers, enabling complex data exchange. However, challenges such as the fragility of quantum states and incompatibility with traditional network components remain. The research used quantum entanglement to enable linked particles to affect each other instantaneously, facilitating secure data transfer. A silicon-based Q-chip was developed to coordinate classical and quantum signals, allowing quantum data to be measured without destruction. Current limitations include the inability to amplify quantum signals over long distances without destroying entanglement, but the study shows progress by routing quantum signals over existing fiber infrastructure. An error correction method using classical signals achieved over 97% fidelity, maintaining quantum coherence in real-world conditions. The Q-chip can be mass-produced, making it feasible to expand quantum networks by connecting more chips and nodes to current fiber networks. This approach indicates that scalable quantum networks could be integrated into existing Internet infrastructure, paving the way for secure communication and distributed quantum computing in the future. Depression has long been viewed primarily as an emotional or psychological condition, but recent research is shifting that perspective. Scientists analyzed post-mortem brain tissue from 59 individuals with depression and 41 controls using advanced genomic techniques. The study, published in Nature Genetics, utilized tissue from the Douglas Bell Canada Brain Bank to examine cellular differences. They found changes in gene activity within two specific brain cell types, excitatory neurons involved in mood and stress regulation, and microglia cells responsible for inflammation management. These alterations suggest disruptions in neural circuits, critical for emotional regulation and immune response in the brain. The research also identified genetic variants in DNA regions that influence gene expression in these cells, providing insight into the genetic basis of depression. These findings could lead to the development of treatments targeting these particular cell types. Ongoing studies aim to understand how these cellular changes impact overall brain function and therapeutic options. Experts highlight that understanding these cellular disruptions might enable more personalized and effective treatments. The study opens new pathways for creating targeted therapies that focus on the affected brain cells, potentially transforming depression management. A new study from University College London reveals that a genomic test can predict which metastatic prostate cancer patients will benefit from chemotherapy. The Decipher prostate genomic classifier, already used in the United States for localized prostate cancer, now has evidence supporting its use in metastatic cases. The research analyzed data from 1,532 patients in the STAMPEDE trial over a median of 14 years. It found that patients with high Decipher scores experienced a 36% reduction in the risk of death when treated with the chemotherapy drug docetaxel. Conversely, patients with lower scores saw minimal benefit from the treatment. The study identified a molecular signature associated with the inactivity of the tumor suppressor gene PTEN, which predicts shorter survival with hormone therapy, but better response to chemotherapy. This finding helps refine treatment personalization by identifying who will benefit most from chemotherapy. Experts say this approach allows clinicians to avoid unnecessary side effects for patients unlikely to benefit, potentially improving overall outcomes. The research was supported by charities, industry, and academia, including Prostate Cancer UK and Movember, and was part of the Cancer Research UK-funded STAMPEDE trial. Prostate cancer remains the most common cancer in England, causing around 12,000 deaths annually, primarily in advanced stages. This study exemplifies collaboration between UCL and Veracyte, combining tumor profiling with clinical trial data to develop more accurate molecular classifiers. Experts believe this advancement will lead to the reclassification of prostate cancer into molecular groups, enabling more effective individualized treatments. A Boston-based MIT spinout has introduced GeMorna, a new generative AI platform specifically designed for creating and optimizing mRNA sequences. This platform produces both linear and circular mRNA molecules with improved expression, stability, and durability, addressing key challenges faced by current mRNA therapeutics. As the first purpose-built AI for mRNA design, GeMorna can generate optimized sequences from a vast design space, speeding up drug discovery and reducing iterative testing. mRNA generated by GeMorna has shown up to a 150-fold increase in therapeutic protein expression, along with higher immune responses in mice and improved CAR T-cell efficacy. The platform has achieved a 5-fold increase in CD19 CAR expression and nearly 100% anti-tumor efficacy in human T-cells. These advancements support the development of mRNA-based vaccines for diseases like cancer, with the platform enhancing immune responses compared to existing vaccines. The technology's ability to significantly boost protein expression highlights its potential in gene therapy and other therapeutic areas. Raina-Biosciences aims to transform mRNA drug development by overcoming current limitations and expanding therapeutic possibilities through AI-driven sequence design. The company has secured early-stage funding, including a $5.7 million angel investment, and collaborates with leading pharma and biotech firms. Founded as an MIT spinout and based in Boston, Raina is positioned to advance RNA therapeutics across multiple fields, including cancer and gene editing, by enabling rapid and precise sequence design. A recent deep-sea drilling expedition beneath the Japan Trench has provided new insights into the mechanics of earthquake and tsunami generation. In 2025, the International Ocean Discovery Program's expedition, 405 drilled over 800 meters into the fault zone involved in the 2011 Tohoku earthquake. Conducted from September to December 2024, aboard the drilling ship Chikyu, this was only the second deep drilling mission in that area. The cores collected revealed layers of sediments and rocks, including slippery clay such as smectite, which can reduce friction and facilitate fault slipping. They also uncovered chert layers that mark the transition to oceanic crust, offering vital clues about fault structure. The data showed that the largest slip during the earthquake occurred just beneath the seafloor, challenging previous assumptions that slip along subduction zones was slow and gradual. This emphasizes the importance of shallow fault zones in generating tsunamis. The Japan Trench Fast Drilling Project previously drilled 850 meters below the seafloor after the 2011 quake and found that the fault was extremely thin and filled with slippery clay, enabling rapid rupture. The recent expedition aims to analyze sediments recording past earthquakes and tsunamis, studying fault slip conditions and water flow that influence seismic activity. These efforts seek to improve hazard assessments and early warning systems by understanding the conditions that lead to mega-earthquakes. The discoveries challenge earlier models by showing that weak zones can produce large, shallow ruptures, significantly increasing tsunami risk. Researchers also examine geological signatures like turbidite sequences to estimate the frequency of large seismic events over millions of years. The insights gained are intended to enhance tsunami hazard assessments and deepen understanding of megathrust fault behavior. Since the 2011 quake, the Chikyu has monitored fault evolution through an advanced borehole observatory, observing real-time changes in temperature and fluid flow to better understand fault dynamics and earthquake conditions. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. We'll be back Monday with everything you need to know.